Hello, this will be a short tutorial about quantum computing using Qibo. So a few slides for the beginning. You have the QR code for the slides, also slides.com Marek Luza, and that's a link to the file that I will be editing. Okay. So first of all, a very quick recap to say that I will show some examples of quantum algorithms. So what we will see is that we will have input qubits. So this is designating the input qubits as a depiction. There will be special qubits that will be doing the control. So the state of this qubit will be switching which quantum algorithm we are applying in a way. That's the meaning of the control. There will be gates that will be coupling two qubits and outputting the two qubits. And there will be single qubit gates. Okay, so this circuit is sort of depicting the locality of where we are applying gates. Gates are basically physical interactions in the system. I will be showing this in a way that might make you think about a quantum computer in a different way. So the cut is depicting quantum effects. And then we have a basket. And in this basket, we have quantum apples, A, and quantum bananas, B. So you can think of a quantum computer as an experimental setup A. We have lots of apples. And inside here, we have some quantum bananas. And those quantum bananas will be our qubits if we get it right. And now the setup A allows us to manipulate the state of this system B. Okay, and now you have a little bit of a black box, a basket with apples and bananas, and you want to make sense of it. That's actually how you get going on building the hardware. And we will be looking at Qibo, which is a simulation software that could control your qubits in the quantum computer. So the vibe will be quite different, similar in the tutorial. Okay, so a universal quantum computer is some system where you have few level quantum systems, and then you can manipulate those quantum states of that those few level systems using gates and couple them together. And these gates form a universal gate set. That's an important term. If you're able to, okay, so let's say you extend this circuit for forever, then you will be able to reach any desired state using only those simple components. So that's the idea of this universal gate set, that it allows you to, in principle, do everything possible. And we will see examples of such gates today. So, so just to tell you, it gets more interesting as you go. So today we will be focusing on few qubits. And the point is that basically the state space is growing very fast. So that's kind of the model numerically behind our circuits that we will be considering today. So it gets pretty large very fast. And basically the circuit model allows you to, instead of looking at such weird numbers, to think more intuitively about it. That's why we think about this. Okay, so quantum gates, just to give you some example, is a way of manipulating the state, for example, of a single qubit, which is in the state 0, and for example, rotate it into the state plus this state here. So we will see how to do it in Qibo in a moment. Okay, so before we will do that, we will check that if we choose some state psi, which is, we believe, 0, and if we choose a operation in Qibo, which we believe is Z, then it will stay and remain an eigenstate. Okay, so now I will do this. So the way to go in Qibo is, here we first install it with pip. And as soon as I have it, I will be also able to install NumPy. Okay, so this is running. It will be installing in a moment. And now we begin by guessing what is the state cat 0. And the point is that in NumPy, okay, there we go. We have the tick here and another tick here. So in Qibo, we can use NumPy to set an initial state. So that's my 0 state. And now we will do the first simplest circuit. And here, here I'm already making a mistake because circuit is not defined. Okay, so from Qibo, we import circuit. And we need to do this from Qibo.models because those are the models for circuits. And now this will be the instance of the class circuit. And we initialize it by telling it how many qubits you have. This is important because we need to apply the circuit to a state ultimately, because the system in the lab also has a state. So you will need at some point a state. So when we will be applying gates, we first need to import them. And then circuit 1 has a way of adding a gate. So from gates, we will add a gate that is called Z, and then we apply it to the first qubit. Okay, that's what I'm doing here. And then to apply it to a state, we just run this. Okay, there we go. Been running it before, but now it's running from the start. Okay, so what we got is that this is 1, 0. So let me show you another trick. We copy this. Circuit 1, 1. And let me do nothing. So let's look at this output. Yeah. So basically it's the same output. Qibo identified our guess for the cat 0 as indeed the 0 state. That's most natural. That's what everybody does. And I guess this is the Q-tip conventions as well. So when we do this, we actually apply Z to it and nothing happened. Okay. So now let me switch this around. 0, 1. Okay. Sorry, there was a typo, but you get the idea. Okay. Now it's working. Okay, so if I don't do anything, I get 1, but if I apply Z, I get -1. Okay, so that's our idea for what states are acting as the 0, 1 states. You can just initialize them in NumPy yourself, and then you get the idea. Those names should be quite intuitive. So Z is, by no surprise, the Z Pauli operation. Okay. So what we managed to do is to apply this. You can try to download the Python notebook using the QR code here. Okay, so let's think about something more interesting. We have the 0 state, and we want to move the state down into the plus state. Okay, we're rotating along of the block sphere onto the X-plane. Okay, and the way we do is to the quantum algorithm that does it applies the Hadamard gate, and you can get this matrix by the regular diagonalization of the Pauli X operator. So that's an exercise that I think almost everybody does in quantum mechanics when discussing Stern-Gerlach experiments. But in quantum information, we are calling this matrix actually we are calling it the Hadamard transform. And here we switch off, and now I can scroll. Here you have iframes for Wikipedia articles in the slides. And here you see H2 is our matrix here. But additionally, we normalize. All right. So that's our matrix. I can do the same thing in Qibo. Okay, so let's see how to do it. We will have another circuit, 2. It will be again a circuit on 1 qubit, so we had this before. And then circuit 2 will be added a gate, and this will be called H. That's the Hadamard transformation. If I scroll here, it should tell me that this is the Hadamard. Yeah, it's seeing gates of this, but okay. So I apply this, and then circuit 2, I can apply again to our cat 0. And I will get already this, okay? So I had this output already before here. And now we could look at the output of whatever we got. And then we could ask for the state. We could tell it to go to NumPy. If you get some troubles, you ask it to output it in NumPy. And then we will multiply this by NumPy square root 2 to see that we have the right amplitude. Okay. Called 2 underscore list? No. Oops. So I just want to remove this NP array. Okay. Okay. So after I multiply with square root 2, this 0.7, which is 1 over square root 2, is changing in 1. We have 0 imaginary part, so it really looks like 1 times 0 plus 1, 0. Okay, that's one way of reading it out. So I would conclude that we successfully applied the Hadamard to a plus. Okay, and now the idea is that the same circuits with a remote access to some hardware, you can apply in a physical state. Okay, so you would be just changing one line in your code, and then this would be dispatched to a quantum computer if everything would be connected, of course. But remote access will allow to do that. Okay, so we have this candidate for a plus state, but we could try to do it using the consistency of our physical operations. And that's this mindset of a black box basket with quantum apples and bananas. Can we apply those things in such a way that they will be consistent? So let's try if we can do this. So I will call a state cat plus here, which will be the circuit to output applied to cat 0. Okay, so that's just our Hadamard on cat 0. And then again, so this is to show you how to store it. So now I will have a state and I will be able to use it again. Okay, so let me apply now an X gate. So you can actually pause and do it on your own to try it out yourself. Circuit 3. So now what do you need to do to apply a gate? You add the gate to the circuit. How do you add an X? You just write X at 0. That will apply to the first one. Okay, that's the conventions. You just need to learn the names at some point and then it will be nice. So X applied to cat plus will be our circuit. And which one? Circuit number 3 applied to cat, not 0, cat plus. Okay, because we are checking what are we getting here. I didn't run here. So Hadamard on 0 should give me a cat plus, so I'm checking cat plus. Now I will be checking whether this is the eigenstate of the X operation. And to check whether this is true, we can again use the null norm X cat plus. Now I will make an error and I show you how to fix it. Cat plus, I think this should give an error. Oh, no, it doesn't. But sometimes if you're comparing things, you have to move them to NumPy. So you would write state of that output, NumPy is true. Sometimes it will fix some issues for you. But a norm is a way of checking equality between the output states. So we checked that the application of what we think is cat 0 with what we think is Z. No, so if we apply what we think is a Hadamard to what we think is 0, and then apply what we think is X, we see that we are getting the same thing. Okay. So this thing is not something you can do directly on a quantum computer. Okay, so I'm making a shortcut here, but I'm trying to show you that you can kind of probe a software like this. So here I describe this a little bit more. You can think about this, and so just let me know if something troubles you here. Okay, I would now move on to the next ideas. Okay, so that's the kind of recap. At the end of the tutorial, at the end of slides, you have the swap test, and the swap test is a way of checking those two things here.